In this episode, we walk through AI incident response as a complete story, from the first signal that something is wrong to the final moment when the organization has learned enough to prevent a repeat. If you are brand new to cybersecurity, incident response can feel like a dramatic, chaotic event where experts rush around and speak in jargon. The reality is that good incident response is a disciplined routine that helps people stay calm under pressure and make smart choices with incomplete information. AI makes this routine even more important because the incident might not look like a classic breach, and it might start as a quiet pattern of misuse or a model behavior change that only a few users notice. When an AI system is involved, you may be responding to data exposure through outputs, manipulation through prompts, abuse of tool integrations, or theft of model access through compromised keys. The goal is not to memorize every possible scenario, but to understand the steps that remain true across scenarios: detect, triage, contain, recover, and learn. By the end, you should be able to describe these steps in plain language and explain what makes AI incident response different from normal IT response. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Detection is where everything begins, and the key idea is that you cannot respond to what you do not see. In AI systems, detection signals often come from three sources: monitoring telemetry, user reports, and business anomalies. Monitoring telemetry might include unusual patterns like repeated prompt bypass attempts, spikes in requests that suggest probing or model extraction, unexpected tool calls, or retrieval of sensitive documents that does not match the user's role. User reports might include someone noticing the model revealed something it should not, gave unsafe guidance, or behaved differently than expected after an update. Business anomalies might include unexpected costs from increased model usage, sudden changes in customer satisfaction, or operational decisions that do not make sense because they were influenced by flawed model outputs. A beginner-friendly way to think about detection is that it is not only about catching hackers, it is also about catching unexpected behavior early. The best programs treat these signals as real security data and route them into an incident process quickly. If detection is slow or ignored, everything that follows becomes harder, because the incident has more time to spread or cause harm. Once a signal is detected, triage is the step where the team turns that signal into a clear understanding of what is happening and how urgent it is. Triage answers practical questions. What is the affected system? Who is impacted? What type of incident might this be? And what is the likely worst-case outcome if nothing is done? For AI, triage needs to consider categories that are not always part of classic IT incident templates, such as prompt injection success, sensitive data exposure through responses, retrieval from restricted sources, misuse of tools connected to the model, or compromise of model credentials. Another AI triage question is whether the issue is reproducible, meaning can it be triggered again easily, and whether it is scalable, meaning can it impact many users quickly. Triage also includes checking whether the incident might be caused by a change rather than an attacker, such as a new model version or a new prompt configuration that altered behavior. That distinction matters because containment actions may differ, even though the impact can be similar. Good triage does not require perfect certainty. It requires clear, time-sensitive decisions based on the best information available. During triage, it is critical to gather the right context without getting stuck in analysis. In AI incidents, context includes which model version and configuration were active, what data sources were connected, whether tool integrations were enabled, and which identities were involved in the activity. You also need to understand the scope. Is the issue limited to one endpoint, one group of users, or one data connector, or is it broader? This is where good logging becomes a lifesaver, because it lets you tie an output or an action to a specific request, user identity, and system state. For beginners, it helps to understand that responders often work under uncertainty, so they use evidence to narrow possibilities quickly. The worst mistake in triage is to assume the problem is small without checking, because AI incidents can look minor at first, and then reveal a much larger exposure when you examine logs. The other mistake is to treat every odd output as a major breach, because that creates panic and waste. Strong triage finds the balance by focusing on impact, exposure, and the ability to reproduce the issue. Containment is the stage where the team takes action to stop ongoing harm and prevent escalation, even while investigation continues. In AI incidents, containment often looks like limiting capabilities rather than rebuilding machines. If the model is leaking data through retrieval, a powerful containment step is to disconnect the retrieval source or restrict it to a safer subset, because that immediately stops further leakage. If the incident involves prompt injection or bypass attempts, containment may include tightening policy filters, increasing detection thresholds, rate-limiting suspicious users, or temporarily blocking certain request categories. If tool integrations are involved, containment may mean disabling tool use entirely or limiting tool calls to a smaller set of approved users or workflows. If there is any suspicion that keys or tokens are compromised, rotating or revoking them becomes urgent, because stolen credentials can allow attackers to continue abuse even after user accounts are locked down. The goal of containment is not to fix everything perfectly. It is to reduce risk fast and create a safer space for deeper investigation and repair. A key point for AI containment is having multiple levels of control, because shutting down the entire system is not always practical. Sometimes you need to keep essential business functions running, so you aim for partial containment. For example, you might keep the model endpoint available but disable access to the most sensitive data connectors, or you might allow only low-risk users while you investigate high-risk usage patterns. You might restrict responses in certain categories until you can validate safety, or you might enforce stronger human review for outputs that can cause direct harm. This is where the idea of blast radius becomes real. You try to limit the incident to the smallest possible area and prevent it from affecting other systems. Evaluating containment effectiveness involves asking whether the system has these control levers built in, because in a crisis you cannot invent them easily. For beginners, it is important to realize that well-designed systems are easier to contain, and containment success often reflects earlier design decisions about segmentation and least privilege. Recovery is the step where the organization restores normal operation in a way that is safe and trustworthy. Recovery is not simply turning the system back on. It is ensuring that the conditions that allowed the incident are addressed enough that returning to service will not recreate the same harm. In AI incidents, recovery can include restoring safe prompt configurations, validating that retrieval sources are correctly restricted, confirming that tool integrations are re-enabled only with appropriate controls, and ensuring that compromised credentials have been fully rotated. If a specific model version or configuration change caused the incident, recovery might include rolling back to a previous version while the new version is reviewed and retested. Recovery also involves validating behavior, meaning testing whether the model still exhibits the dangerous or undesirable behavior that triggered the incident. This validation should be evidence-driven, using reproducible test cases rather than hope. A strong recovery process defines criteria for declaring the incident resolved, such as no further leakage in monitoring, no successful bypass in test prompts, and stable system operation under normal load. While containment and recovery are happening, investigation continues. And an AI incidents investigation often involves understanding the interaction between inputs, model behavior, and connected data. Investigators might review logs to see how the incident was triggered, what prompts were used, what documents were retrieved, and whether the model took actions through tools. They may also look for signs of systematic probing or extraction, such as repeated variations of prompts or high-volume structured queries. Another investigation angle is to determine whether the issue is malicious or accidental. For example, a user might accidentally paste sensitive data into a prompt, and the incident is about data handling and training, not about an attacker. Or a model update might have weakened safety boundaries, creating an exposure without any adversary. Even when the cause is not malicious, the response should still be treated as serious if the impact is serious. The key is that investigation should support decisions, not become an endless search for certainty. The team needs enough understanding to fix the problem, contain risk, and document what happened. Learning is the stage that turns an incident into improved safety, and it is where problem management connects back to incident response. After the incident is stabilized, the organization should perform a post-incident review that identifies root causes and contributing factors. Root cause might be a missing control, such as overbroad retrieval access, weak monitoring for prompt abuse, or shared service account credentials. Contributing factors might include unclear ownership, lack of testing for known abuse patterns, insufficient documentation of model changes, or pressure to deploy quickly without review. Learning also means converting lessons into actions, such as tightening access controls, adding new monitoring rules, improving change management for prompts and model versions, and expanding adversarial testing coverage. A good learning process assigns owners and deadlines and verifies that improvements are implemented, rather than leaving lessons as recommendations that fade over time. For AI, learning should also include updating detection and playbooks, because attackers and failure modes evolve, and the organization must evolve with them. Communication is woven through every stage, and it matters because incident response is a team activity with real-world consequences. During detection and triage, responders must communicate clearly about what is known, what is unknown, and what decisions are being made. During containment and recovery, they must coordinate technical changes and keep stakeholders informed about operational impact. Afterward, they must communicate lessons learned in a way that improves the system without assigning blame. AI incidents often involve sensitive information, so communication must also be careful about who receives what details. This includes internal stakeholders like legal, compliance, and leadership when necessary, and sometimes external stakeholders like customers or regulators depending on the nature of the incident. For beginners, the takeaway is that strong incident response is not only technical skill, but also disciplined communication under stress. The clearer the communication, the faster containment happens and the less likely the response will create new problems. As you conclude, remember that AI incident response follows the same core stages as other incident response, but the content of each stage is shaped by how AI systems behave. Detection often relies on interaction patterns, user reports, and monitoring that focuses on prompt abuse, retrieval misuse, tool call anomalies, and credential misuse. Triage must consider whether behavior changes are due to adversaries, configuration changes, or model updates, and it must focus on impact and scalability. Containment often involves restricting capabilities, disconnecting data sources, disabling tools, and rotating secrets quickly to stop ongoing harm. Recovery requires restoring safe configurations and validating that unsafe behaviors are no longer reproducible. Learning turns the incident into improved controls, monitoring, and governance, so the same class of incident does not recur. When you can explain this flow clearly and connect it to real AI failure modes, you have a strong foundation for understanding how organizations keep AI systems safe under real-world conditions.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.